Welcome to this instructional video from Vixos. This is part 2 in a small series where we explain how to understand the SORA step number 9 on adjacent airspace and adjacent ground area. In this video, we will take a look at the probabilities involved in step number 9. We want to show how to interpret the different numbers and the statements about reliability of the drone. If you have not watched part 1, I recommend that you do that before continuing with this video. There is a link to the video in the upper right corner, and you can also find all parts of this video series on our website at vixos.dk. Let us start by quickly revisiting the requirements in step number 9. First, there is the operational volume where all your operations are supposed to take place. The airspace outside this volume is called the adjacent airspace. This is where all the other airspace users would be. Around the operational volume, we find the ground risk buffer, and outside of this buffer is the adjacent ground area. Step number 9 has the following requirements. When you operate your drone, there is a certain risk that you will have a flyaway where the drone breaches the operational volume and the ground risk buffer. Step 9 part B states that the first breach should happen less often than once per aircraft lifetime, while Step 9 part C states that the first breach should happen less often than once per 10,000 flight hours. In addition to this, part C also states that no single failure on the drone must lead to a breach of the ground risk buffer. Remember also that part B applies always, while part C applies only for some operations. For details on this, do see the first video in the series. These requirements raise 4 questions. 1. What does 1 per 10,000 flight hours mean? Does it imply, for instance, that your drone simply cannot crash in the first 10,000 flight hours? Question 2. How can you demonstrate 1 per 10,000? Is it necessary to actually fly for 10,000 hours to demonstrate compliance? Question 3. How often is once per lifetime for any given drone? And question 4. What is meant by a single failure? We will start with question 1. What does 1 per 10,000 mean? First, here's your drone, and here's the timeline that goes from 0 to 10,000 hours and beyond. So you start using your drone and conduct many operations until one day you have a flyaway. Let us say that happens after 4,500 flight hours. This is clearly less than 10,000 flight hours, so the question is that a violation of the requirement that a flyaway must happen less often than once per 10,000 flight hours? Well, not necessarily, because 1 per 10,000 is an average, and it is to be understood in the following way. Imagine that we have a somewhat longer timeline that goes to several times the 10,000 flight hours, in this case to 50,000 flight hours. You are using your drone and accumulating flight hours, and occasionally you have a flyaway. These are the small explosions shown on the timeline here. Imagine that the drone survives each of them and that you can keep flying and accumulate more hours. When you now look back at the 50,000 flight hours, you count the total number of failures, which in this case is 5, and you divide that by the total flight time that the drone has accumulated. In this case, this would be 50,000. If this number is equal to 1 divided by 10,000, then your drone has the required reliability, even though the first failure, the first flyaway, happened way before reaching the first 10,000 flight hours. This calculation was done using a single drone, and it may seem unrealistic to ever accumulate so many hours in just one drone. But the concept applies to multiple drones as well, as long as these are identical. So imagine that you have 4 drones flying simultaneously. Here the drones have already jointly accumulated about 2,500 flight hours. And you now let them fly at the same time, doing operations in parallel, until they each have 2,500 flight hours, which jointly of course is 10,000 flight hours. The 1 over 10,000 requirement can now be satisfied if, on average, only one of the 4 drones has a flyaway failure for every jointly accumulated 10,000 flight hours. Yet another way of understanding the 1 over 10,000 requirement is as follows. You go to the flight area and conduct a full day of flight operations. Let us say that this takes 5 hours of airborne time. Then you go home and come back the next day. And you fly for another 5 hours. You go home again and you come back again for yet another 5 hours of flight. And you keep flying 5 hours a day, every day for a long time. In fact, you keep doing this 2,000 times over. Because 5 times 2,000 is exactly the 1 over 10,000 requirement. If you fly on weekdays, it takes almost 8 years to accumulate the 10,000 flight hours with one drone. We can therefore also say that if you fly 5 hours a day and only have, on average, one flyaway every 8 years, you comply with the 1 over 10,000 requirement. We previously illustrated the requirement using 4 drones. And a common question is therefore, if I have 4 really good drones that easily comply with the reliability requirement, but one of them seems to have problems with the compass, is it then possible to use 3 good drones to jointly reduce the probability of a flyaway for all 4 drones? No. The reliability requirement applies to every drone independently, even if we conceptually distribute the 10,000 flight hours on multiple drones. Because this only works if the drones are identical. Well then, what if we have 4 really good drones and also 4 operators, but one of them is new in the company and has not yet received all the necessary training? Again, the answer is no. The reason is that the reliability requirement applies not only to the drone, but also to the operator and to the ground control station and to the radio. In fact, the requirement applies to the entire system. We will now turn to question 2 on demonstrating 1 over 10,000. And you may wonder, how will it ever be possible to show a probability of only one failure for every 10,000 flight hours without flying for 8 years? To get a sense of how this can be done, consider a line of events that can lead to a flyaway. On the left here, everything is fine. And then a series of events leads to a flyaway where the aircraft is leaving the operation volume. A typical series of events would be as follows. The first event is loss of control. This means that the operator can no longer make decisions on where the aircraft goes for whatever reason. Loss of control include no radio contact, loss of controllability due to a stock servo, loss of navigation due to a faulty sensor, no response to commands due to failure in the autopilot software, loss of lift due to engine failure, as well as numerous other failures. In most cases, the loss of control will make the aircraft descend to the ground, which obviously prevents a flyaway. So an additional event that needs to happen on the path to a flyaway is that the aircraft does not descend as a result of loss of control. But typically it will descend. For instance, it may return to land, fall from the sky, make a safety descent, or perform an on-power glide or auto-rotation. But if none of these happens and the aircraft keeps flying, it is quite likely that the aircraft is heading out of the operational volume. This will be a good time to activate the flight termination system. However, in the event that it does not work, or in the event that you never installed it, the aircraft is probably going to leave the operational volume. So to get from everything is fine on the left to leaving the operation volume on the right, these 3 events needs to happen. Loss of control, followed by no descent, followed by the flight termination system not working. Therefore, in order to prevent a flyaway, we want to prevent each of these events. And for each event, we have a barrier, meaning that we have procedures and mechanisms in place to stop these events from happening. For example, for preventing loss of control, we do a check of the aircraft before we fly. To prevent the aircraft from not descending, we activate the return to home functionality. And to ensure that we can terminate the flight, we install and test a flight termination system. We are now getting close to computing the probability for a flyaway. So let us assign probabilities to each of these events. The probability of loss of control we will call PLOC. The probability for not descending in case of loss of control we will call PND for not descent. And the probability for the flight termination system to fail we will call PNFT. Since all three events need to happen for a flyaway to happen, we can multiply them to get the probability of leaving the operation volume. This multiplication does require that these three probabilities are independent. For example, the use of a flight termination system must not depend in any way on whether we have control of the aircraft. So for instance, if the flight termination system is commanded via the autopilot, this formula cannot be used because a loss of control due to autopilot failure will then affect the ability to do the flight termination, which again means that PNFT and PLOC are not independent. So do make sure that these three events are truly independent on your platform. Okay, let us now assign some numbers to these probabilities. Taking the easy one first. We know from step 9 that PLOV must be 1 over 10,000 flight hours. For the other three, it obviously depends on the platform, the procedures, the training, and so on. Still, for loss of control, we will conservatively set this to 1 over 25 flight hours, which means that the event loss of control will happen once for every 25 flight hours. Now, this may seem low, but keep in mind that this includes fairly frequent events like loss of radio contact, erratic flight because the compass was not calibrated in a new location, and flight in too high wind speeds. Next is PND, the probability of not descending if a loss of control event happens. In most cases, the aircraft will come down, but not always. For instance, loss of control due to the high wind or because the autopilot has a software malfunction or the home point is set incorrectly when radio contact is lost may all have the consequence that the aircraft does not descend, at least not inside the operation volume. A reasonable estimate of PND could therefore be that for every 10 loss of control events, one of them will not result in the aircraft descending. Finally, we have the PNFT, the probability that the flight termination system is not working when you have both loss of control and no descent of the aircraft. But since we only have one variable left in the equation, we can also compute what PNFT needs to be. In this case, it must be 1 over 40, meaning that the flight termination system can only fail once for every 40 times it is used. Note here that if the aircraft is not equipped with flight termination, this probability becomes 1, and since the probability of not descending is probably hard to change, the probability of loss of control must then be as low as 1 per 1,000 flight hours to still give a flyaway probability of 1 per 10,000 flight hours. Since this is rather unrealistic, it is difficult to comply with step 9 without having a flight termination system. Let us move on to the third question. How often is once per lifetime, the term used in part B in step 9? This question boils down to, what is the lifetime of a drone? Is it 50 flight hours, 100, or what? It is important to note that lifetime is not defined by how long it actually lives. So things like a crash or severe damage, the drone becoming obsolete or require extensive maintenance to keep flying does not count. Rather, the lifetime means how many hours of flight the aircraft can achieve and still have airworthiness, on the condition that it is always operated according to manufacturer's instructions and that all scheduled and required maintenance is done and done properly. So then, what will end the life of a drone? Well, just like many other types of machinery, operating it will slowly wear it down. Stress and vibrations will ultimately take its toll until the point where the fuselage or frame itself is no longer airworthy. But how long is that? For smaller drones, a good indicator of this is the warranty from the manufacturer. It is typically a 1-year warranty, but if you read the fine print, there's often also a limit on the number of flight hours. For many drones, this is something like 100 or 200 hours. But this is just the warranty, and just like a car can easily outlive its warranty, so can a drone. And therefore, the lifetime is likely to be somewhat higher than the warranty. For the bigger and more expensive drones, there is typically a contract signed, which will often directly specify the lifetime of the aircraft, which will likely be at least 1,000 or 2,000 hours. Finally, we have the question, what is a single failure? We will answer this with an example looking inside the drone. Here is the radio module that communicates with the ground control station. It relays the received commands to the autopilot. This drone also has a flight termination system plus parachute, which are both activated via the autopilot. But what happens if the autopilot has a failure where the drone keeps flying but is no longer able to communicate? Well, the flight termination system has now stopped working because it can no longer be activated. And therefore, in this setup, a single failure, namely a failure of the autopilot, can lead to a flyaway. According to Step 9 Part C, this is not allowed since no single failure must have the ability to cause a flyaway. So how can we fix this? We can have a separate communication link for the flight termination system, for instance through satellite. We can use this to independently activate the flight termination system, and therefore we no longer have the autopilot as a single point of failure. Now, do keep in mind that this is one example. To comply with Step 9 Part C, there must not be any single points of failure for a flyaway. We have now examined all 4 questions on probability, so let's do a quick recap. Question 1. What does 1 per 10,000 mean? It means that on average there can be at most 1 failure for each 10,000 hours flown, and the required reliability applies to the entire system, not just the airborne platform. Question 2. How can you demonstrate 1 per 10,000? You can use a model of events that can lead to a flyaway and multiply the probabilities to show that you can reach 1 over 10,000. Make sure to be realistic when assigning probabilities to each event. How often is once per lifetime? For the smaller commercially available drones, the lifetime would typically be 500 to 1,000 flight hours. For the larger professional systems, it will be several thousand flight hours. Question 4. What is a single failure? If there is one component in the drone which can lead to a flyaway if it fails, then we say that the drone has a single point of failure. From the team at Vixos, we hope you found this video useful and you now know a little more about the SORA step number 9. If you're interested in seeing more Vixos videos, do visit our website at vixos.dk.